Hey, welcome back to another round of astronomy. Right? You excited? You ready for it? All right. So I'll say just on the top, we'll talk about black holes today and the research and the amount of discoveries that have been coming out in the last 5 years or so has been so fast, so much that frankly, I think that there's a lot of great video resources out there already. If you find one that's great, please send it to me. I just have this continuing list of these kind of things going on. So I'm going to rewind the clock. We're going to go back almost, oh shoot, what is it? Probably about 270 years. 270, that's not quite right. 240 years. Okay? So I'm going to go back. So let me go ahead, and this is John Mitchell writing to Henry Cavendish. I have to look up what Mitchell did. I don't know for sure. Shamefully. Boom, fly out. So let me read this quote to you. If the semi-diameter of a sphere of the same density of the sun were to exceed that of the sun in proportion of 500 to 1, a body falling from an infinite height towards it would have acquired at its surface greater velocity than that of light. And consequently, supposing light to be attracted by the same force in proportion to its inertia with other bodies, all light emitted from such a body would be made to return towards it by its own proper gravity. I don't know, I'm always fascinated. This is 150 years before Einstein's general relativity, and they're describing a black hole. Let's fast forward. Okay? This is 10 years after Einstein's general relativity. Arthur Eddington was another astronomer. I believe he studied the collapse of stars. Okay, so that's why he has this black hole quote. Let me go ahead and read this to you. Referring to Betelgeuse, so in Orion. It is rather interesting to notice that Einstein's theory of gravitation has something to say on this point. According to it, a star of 250 million kilometer radius could not possibly have so high a density as the sun. Okay. First, the force of gravity would be so great that light would be unable to escape from it, the rays falling back to the star like a stone to the earth. Secondly, the redshift of the spectral lines would be so great that the spectrum would be shifted out of existence. I'm going to highlight that last part, okay? The stone part we've already discussed. Okay? But I like this idea of the redshift. Okay? So one way we could think about it is throwing a stone up from the surface and it returns back down to the ground. I think that Eddington produces a second way to think about a black hole. You have a massive object. That massive object, because it is so massive, so dense, might be a better way to say it, is that it stretches space-time, just like that bowling ball on the trampoline. If you have a dense enough object, it will stretch space-time, it'll stretch space, okay? And it stretches space so quickly that the space gets stretched faster than the speed of light. Okay? That should sound a little familiar. Okay? If we go back and think about when we were measuring the size of the universe, remember we said there's this cosmic event horizon, this point centered on the Earth, or I should say a distance from Earth, beyond which space stretches faster than the speed of light. Here we have another idea about that. Okay? So if you take a dense object, it stretches space-time so much, so quickly, that light can't keep up. It's running on that treadmill again. And so you could think of the black hole as emitting light. Say, I'm a black hole and I emit light upwards. Okay? That light travels. And since space-time is stretching so much because of me, that light goes to longer and longer and longer wavelengths. It keeps getting stretched, redshifted, 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 until it fades out of existence. That's a different way of thinking about this black hole. Consequently, one of the things that we use to describe a black hole is called an event horizon. Just like we use the term event horizon to describe the limits of what we can see in the universe. Okay, cool, right? So let me give you some ideas. Okay, this is 1926. We have not observed black holes, but we have some good indications, some good observations which agree with Einstein's predictions. So we have general relativity, and now let's go through and talk about some of the observations which general relativity can explain. So one of them are these X-ray and radio emissions. Okay? Imagine for a moment that we have a black hole. Okay? And what I'll play for you here is a black hole, and it's out in space, and a star happens to wander close to it. Okay? So you have a black hole, a star wanders close to it, and what happens is, if it's close enough, that black hole will suck in that material. It will accrete that material. Now you have the situation. Okay? Now, please bear in mind, this material is not inside the black hole. I'll play it one more time. Okay? Rather, what happens is that material of the star falls towards the black hole. Its kinetic energy goes up, right? It's trading gravitational potential energy with kinetic energy. Okay? And so as the material falls towards the black hole, it heats up. Okay? That gas, the kinetic energy of the gas goes up, and we interpret that as a higher temperature. Okay? So as it falls closer and closer and closer to the black hole, it heats up. And because it's at a high temperature, it emits light. It gets so hot, millions of degrees, that usually right before entering that point of no return, the event horizon of the black hole, it's usually emitting X-rays. That's how hot it has gotten. So a black hole itself does not emit light. Material that is in the process of falling into the black hole does. Okay? So that's one way that we can get an idea about whether there might possibly be a black hole somewhere. We look for these very strong X-ray sources. As it turns out, I also put radio waves in here. The reason that we use radio waves, again, is because radio waves pass nicely through a lot of the gas, dust, other material that might be between us and the black hole. So you notice also, and I'll point this out, although we won't go too much into detail about it, you might hear terms of blazars or radio, active radionuclei, galaxies, galactic, blazars and pulsars and yada, yada, yada. Okay. This is also related to the black hole. Sometimes what you get is what's called a beaming effect. Okay. According to our models of astronomy, black holes are about the only thing that could produce such energetic beams. Well, that's not the only thing. That's just a hint. Okay? How about stellar orbits? Okay? And I've got the rest of these. We've got three more. We'll talk about stellar orbits, gravitational waves, and finally, la pièce de la résistance, direct imaging. Okay, buckle up. Here we go. So, stellar orbits. Let me walk you through this diagram. Okay. What we are looking at is a path, trajectory of about 7 or 8 stars. Okay. Now, we're looking towards the Milky Way center. Okay. What we call this is Sagittarius A star. The dots correspond to actual observations. Now, please bear in mind, this observation group, this pattern, took about 20 years to collect. Can you imagine 20 years just to get this? But that was a sufficient amount of time. That's how long they needed to get enough dots so that they could trace out the full orbit. The more observations you get, the more certain you can be about the orbit of these various stars. So why do we need multiple stars? We want to be able to find out where is the gravitational center of this collection of orbits. So we've been able to identify a couple of things. First of all, how fast the stars are moving, and second of all, where the gravitational center is. And we've identified that the gravitational center is about 40 astronomical units in diameter, give or take. Now, we also have a good conceptualization of gravity, whether it be Newton's laws or, if you want to use the more advanced, Einstein's equations, general relativity. But if we just go ahead and we apply, actually, you could probably do Kepler's laws as well. If we go ahead and apply something similar to Kepler's third law, we are actually able to figure out that the center object, which is no larger than 40 astronomical units, has something like 4 million solar masses. Okay. The only object that we can think of, according to our current understandings, that could have that much material in such a small volume of space, you guessed it, is a black hole. So this again is indirect observational evidence. Okay. We see the orbits of stars. We have an idea about how fast they are moving and how large the gravitational center is. And based on those ideas, we can estimate the mass of the central object, about 4 million suns. Incidentally, I should also point out, when we turn our telescopes there, we don't see anything. So not only do we see these stars orbiting some mysterious center, but when we actually examine that central object, we don't see anything there. There is no bright light coming from that area. Okay. Let me get you to, okay, so that's the second one. The third indirect observational evidence is what are called gravitational waves. These gravitational waves are so, the intensity of these gravitational waves, the observed brightness, if you will, is so low that we really need these two things to be moving quickly and actually generally speeding up. And the way that that happens is when the two objects spiral into each other. Right before that spiraling, these gravitational waves are just barely intense enough for us to measure here on Earth. Right? You could say, well, why is that? Well, that's because these mergers occur so far away, and you know that the intensity, or the brightness if you prefer, drops according to the distance to the object squared. Right? That in brightness luminosity relationship. Okay. So we have that idea. Now let me give you, so this is what we're trying to measure, these gravitational waves. Let me now play a video about how do we actually do that measurement. The previous video, this demonstration, mentioned LIGO, the Laser Interferometer Gravitational Observatory. There we go. Laser Interferometer Gravitational Observatory. This is actually a pair of two facilities, one in Louisiana and one in Washington State, that are designed to try to measure these small ripples of the gravitational waves. We have two facilities, partially because these ripples, the intensity of these gravitational waves, the brightness, is so small that even just a tree falling in the forest could bugger up the measurements. So what we do is we have two facilities located very far away from each other, and they both have to register the gravitational wave in order for us to gain confidence that it was indeed a wave. Okay? It wasn't some tree falling in the forest of Louisiana or some car crash in Washington state. I have for you right now, shown here, were as of 2017, the gravitational waves that were measured and representing two black holes that merged, that spiraled in. Okay? The first black hole merger ever detected, I'll have to go back and look, but I believe it was something like 4 solar masses converted instantaneously into pure energy. These gravitational waves are generated, first of all, by the kinetic energy of the two black holes. But right when they merge, there is a sudden conversion of some mass into the energy of the waves, the gravitational waves that radiate outward. Right? So the first black hole merger, it was about 4 solar masses that were instantaneously converted into these gravitational waves. So as of 2017, there were 2 facilities that actually made these measurements, one in Louisiana, one in Washington. And of course, one way that you confirm that you've seen a black hole merger is that you have to actually see that signal in both detectors. Now, in case there's some, I'll point out to you here, small byline, they process the data independently. Okay. By that, I mean, when you have essentially only 2 facilities that are doing these measurements, you want to make sure that there isn't some sort of scientific bias. In other words, that a scientist sees both of the data sets and says, oh, that must be a black hole. Okay. You look at the data and want to see the result, and so then you actually see it. Okay. So what do? The facility in Washington sees the data and processes it and identifies potential black hole mergers in the data. Okay. The group in Louisiana does the same thing without talking to the group in Washington. So this is what we would call a blind analysis. The 2 parties do not correspond with each other. Okay. Then, after they identify potential black hole mergers according to just their data, then they come together to see if they both agree. So they process the data independently, they identify what they believe are black hole mergers, and then they merge the data. They look at the data side by side to see if both facilities have identified the same events. That happened the first time, I believe, was in 2016. They processed the data in Washington, they processed it in Louisiana. They identified independently an event, which they believe was a black hole merger. Then they came together and found that they both identified the same event. Then, of course, you model it with Einstein's general relativity, yada, yada, yada. Pretty cool, huh? Now, the fact that there's 2 separate facilities, okay, also helps us triangulate where in space these black hole mergers occur. If the signal happens to reach the Washington facility before the Louisiana facility, that gives you an idea that the black hole merger was closer to Washington than Louisiana, and gives you an idea about the direction that you should be facing in order to see this event. So that's what this image down here represents, is that because we have 2 facilities, we are able to roughly triangulate the position in the sky for various events. Each event is labeled in a different color. Okay? And you notice that the region of the night sky covered is rather large. The reason for that is because originally we had two facilities, and since then there is a third facility, I believe it's called Virgo, that has opened up in Italy. And there are, I believe, two more facilities that are in the process of being constructed or in their ramp up stage. In other words, they're constructed and they're now working out the kinks to become operational. So I believe that there's about 5 facilities either currently in operation or will be soon in operation. And the more facilities that become available that start doing these data collection, the more refined, the more precise we can be about the location of a black hole merger in the sky. So stay tuned. In fact, I'll put one up right now. What you're looking at is a more, because there are more facilities measuring these black hole mergers, we can be more precise about the location in the night sky where these mergers occur. Cool, huh? To recap, okay, we have X-ray sources. Okay. Number 1, we have observational evidence of stellar orbits that would suggest a really massive object in a very small amount of space that does not emit light. Okay. We now have observations of gravitational waves, what we believe to be 2 black holes spiraling in towards each other and combining. Okay. What we did not have as of December of 2018 is direct observational evidence. We have some ideas about what a black hole should look like if we could actually take a picture. If you notice, this is the black hole gargantuan from Interstellar, the movie. You might say, well, why am I talking about movies right now? Keep in mind, there was a scientific advisor on Interstellar. He actually read through the script, okay? And everything you see in Interstellar is not explicitly forbidden according to our current models. Let me walk you through it. So as talked about, generally black holes will suck in material from neighboring stars, clouds of gas, et cetera, and that material heats up. It releases visible, not only visible light, but X-rays as well. Okay? So this is the accretion disk that you see kind of wrapping in front and coming in front of the black hole and then going behind. Okay. Now you might say, well, what is this vertical disk that you see here? Okay. Kind of surrounding here. Okay. What you are seeing is the warping of space by the black hole. Now imagine this accretion disk comes around in front and it should go off behind the black hole. Okay? So it should go behind the black hole. What you have is light coming from behind the black hole, and if it's just above or just below the center of that black hole, it will actually bend around and be focused on the front side. Okay? So what are you seeing here? This light that you see coming from the top of the black hole is actually coming from the accretion disk behind. It's traveling above the black hole and being bent around to come back to the front. Same thing from the bottom. Okay. So this vertical disk is actually light coming from hot material behind the black hole and being gravitationally focused back in front. Pretty cool, huh? Now, that's what we expect. That's kind of what we expect to see, simulated. Now we have to talk about how would you actually make that measurement? How would you make that observation? And that is what's called the Event Horizon Telescope. It is a telescope designed to image directly the event horizon of the black hole. Remember, we can't see the actual black hole itself. What we can see is the material falling into the black hole. Ready for it? Let me give you a zoom up of the black hole that was first imaged. Okay? The reason for this, although M87 is a lot further away than our center of our own Milky Way galaxy, Sagittarius A star. There's two things. First of all, M87 is particularly active. We'll see the jet in this video. The second issue is that because of the relative mass of the black hole, it turns out that it's easier to image this black hole because it's so much larger than Sagittarius A star. So it's particularly active, and it's a lot larger, so that its angular size is actually greater than Sagittarius A star. Okay? It's further away, but it's so much larger that its actually angular size is larger, which means it's easier to see. I mean, we know that we suspect that these things exist, but we finally have direct evidence, and this is it. You notice that the bottom side is a little bit brighter than the top. That just says that the material on the bottom is coming towards us, whereas the material on the top is moving away. Okay? It's that red shift versus blue shift kind of thing. Okay? Let's go ahead. Okay? Cool, right? Yeah. Okay. So that's really all I have. I mean, I'm telling you, here's how we actually find the black holes. Here's, observational suggestions that can be explained by general relativity. But we finally have our first one. And stay tuned. The Event Horizon Telescope has taken data for Sagittarius A star. It's just that there's two things. Because the relative size is so much smaller, they had to take longer observation times, number one. And so they're still processing the data. Hey, when you're a huge project like this, you go for low-hanging fruit first. Okay. So stay tuned. Hopefully, in the near future, we'll have an image of our actual black hole for the Milky Way as well. Okay. Very cool. Hey, that's it. Hey, thanks for your attention, all the hard work during the semester. I know that we've had to deal with some bumps and bruises, but we made it through. I'll see you next time.